So now we will start the session. So this is our lecture 4 of rotational motion. First of all, we will recall some basic phenomena, basic concept about direction of torque. What you have studied is that torque is what? We have studied that torque is nothing but R cross F. Here R is the position vector of the point of application of force and F is the force. So now what is the direction of torque? If someone asks you how to find the direction of torque, then you can clearly or directly say that the direction of torque is decided by the direction of R cross F. If you can find this product R cross F, then you will be able to find the direction of torque. Okay, let's just give me 1 more minute. Actually, I think YouTube So now what we have done, this is the direction of torque. How can we decide? Using the direction of R cross F, and it can be decided by right hand thumb rule. Right hand thumb rule. Now there might be some situations. For example, if I say, like there are two rods on your screen. Rod 1, this rod is hinged at its center. Hinged means that it can rotate about this point. It can rotate about this point freely, like this one. This is the rod hinged about the middle point, and it can rotate like this and this and this. Okay. So now what I did, I have applied a force. Have a look at that. This small force F is applied, F1 is applied on it. Can you guess in which direction this rod can rotate? Yes, you are right. The direction you can predict here is like this. The rod will tilt like this now, and you can say it has rotated in the clockwise direction. In the clockwise direction. Now again, on the second rod, which is also hinged at the center, I have applied again a force F2. Then can you guess in which direction it will rotate? Yes, it will rotate like that. So it is rotated in the anti-clockwise direction. Can you say that this is anti-clockwise direction? So force has rotated the rod, and the direction of rotation, in one case it is clockwise and in other case it is anti-clockwise. So what we can do here, as torque is a vector quantity, we need to assign some sign convention to it. We need to assign some sign convention to it. So what we are going to decide, that the clockwise rotation, the force which is rotating the rod clockwise or the body in the clockwise direction, we take that torque as a positive torque. So this torque we are going to consider as positive, and this torque we are going to consider as negative. Is it clear to you? I hope this first point is very much clear to you. Again, moving further, talk about the axis of rotation. This is another big thing, and that's what we are going to use more frequently as compared to what we have studied in R cross F form. I think this is clear now. Okay. Now, talk about the axis of rotation. What we can do here? I will summarize you. I will give you few points. Like, listen. Suppose this is a door. Door at your main entrance gate or wherever in your room there is a door. So have a look at this door. This is the handle of the door, and this is the line about which it will rotate. The hinges about which doors will generally open and close. So when we talk about axis of rotation, what we have studied that torque about an origin O, like this one, like this one. We have studied that only. So now we are going to study torque about an axis, not about a point. So in that case, there are 3 or 4 possible situations that you can easily remember. The basic concept is that you can calculate, you can choose any point on the axis, like this point or this point. You can choose any point on the axis, calculate the torque about that axis. This is the basic thing that I am telling you. After that, I will give you some punchline so that you don't need to remember everything else. First thing basic is choose any point on the axis, calculate the torque about that axis, about that point. For example, you have taken a point O, you have taken an origin at O. You can choose any point here. Calculate the torque of the force. For example, force is here. This is the force F. Calculate the torque of this force about O, like R cross F, as we have done it yesterday's class. So after that, what you need to do, take the component of this torque. Remember, listen to me. Take the component of this torque about the line AB, and that will be your given, or that will be your resultant torque about axis. First step is, what is the step one? Choose any point as origin on the axis of rotation. Clear? First step is clear. Any point. You can choose any point. Second step is calculate the torque of the force about that point. Calculate torque of the force about that point. Now the main step came. Third step. What it says? It says that take the component of that torque that you have calculated. Take the component of that torque about the axis AB. Is it clear? These three steps, these are the basic steps. So now I don't want you actually to do all these stuffs. So I have decided to put three punchlines, and in three punchlines, you can easily solve the questions. Hmm. Listen to those punchlines. Those punchlines are very important. Actually, I think there is an issue with the YouTube live today. I don't know what might be the case. Give me one more minute, actually. Okay. So sorry for the interruptions. Actually, uh, so now the three punchlines that we are going to discuss about. If first punchline says if F is parallel to AB, F is parallel to AB. First of all, AB is what? AB is our axis of rotation. Now suppose I have applied a force here. This is the force that I am applying. Suppose this is the force. And this force, can you see that is parallel to the axis of rotation? Now, can you again see that if you apply force on your door, like in this situation, then door will not open actually. So one thing that we need to remember, you can make it a punchline in your mind that if F is parallel to AB, then torque of that force is zero. Torque of that force is zero. Second case, remember those things. These are very important things. Second thing, if F intersects AB, for example, if you applied a force like this force is going to intersect the line AB like this. Or you have applied some force here like this. This force is again going to intersect the line AB. That means these forces are in the same plane of the door. These forces are in the plane of the door. So again, torque will be zero. Two things that I have told you. One thing, if F is parallel to AB, then torque will be zero. Second thing, if force is going to intersect the line, going to cut the line, then the torque will also be zero. Third case is if F is perpendicular to AB, but does not intersect. This is another very good thing. Force is perpendicular to the line of axis of rotation, but does not intersect. How is it that possible? Is it possible? Yes, it is possible. Can you see that? Can you see the situation here? Just imagine. Just imagine that door is in the XY plane. And the axis is what? Y axis. Now, listen to me. I have applied a force in the Z direction. Now imagine line or the axis of rotation is along the Y axis, but the force is in the Z axis. Can you say that both these things are perpendicular to each other? Both these things are perpendicular to each other. Now this thing is clear to you. Now imagine, suppose this is our axis of rotation. Let me remove the blur here. Now, can you see that? This is our Y axis. And the force, this force is in the Z axis, like this. They are not intersecting. Force is acting at this point. Axis is in this direction. They are perpendicular, but they are not intersecting. Such lines are known as skew lines. Such lines are known as skew lines that do not intersect each other. So in this situation, the torque will be what? Torque will be force into mutual perpendicular distance of, can we write AB as the axis? So I am just writing AB. AB means axis of rotation and the line of action. And the line of action. So how can you calculate the torque? You just need to find the mutual perpendicular distance between the axis and the force. Now in this case, can you see that axis is along AB, force is along acting at this point like this in the Z direction. So the mutual perpendicular distance is what? This is the mutual perpendicular distance. So we can write it as R perpendicular. So tau is F into R perpendicular. This is what the basic idea behind the torque about an axis. I think it's clear. All other cases you can do with the basics if it requires. Now moving further. Now the next situation is What does it say? Newton's second law in rotational motion. What is the Newton's second law that we have studied in linear motion? It was F is equals to ma. You remember? You remember now? In linear motion or in translational motion, what we have studied that F is equals to mass into acceleration. Now, in translational key space पर if I write in rotational motion, what are the things that will change in rotation? One thing that you know that in rotational motion, we consider rotational motion is what? When there is an angular acceleration, there is angular velocity. So all these things are produced by torque. So what is the correspondence or what is the corresponding phenomena of force in rotational motion? That is torque. So this force will be replaced by torque. One thing is sorted. Second thing, the mass of the body is just what? Inertia. Mass is what? Mass is called as inertia, linear inertia, translational inertia. So now, if I replace it in rotational motion, what is rotational inertia? You have denoted it with I. You have denoted it with I. I is called rotational inertia or moment of inertia. Now, another thing is acceleration, A. A is what acceleration? In rotational motion, acceleration is denoted by alpha. So the relation is tau is equals to I alpha. This is the rotational second law of motion in rotational motion. I know that all the meanings of these symbols are clear to you. Tau is the torque, I is the moment of inertia, alpha is the angular acceleration. I think things are sorted. Moving further. Now, one more thing, you can consider it as a punchline because it's a previous year. I'm sorry, previous year. It's about previous chapter thing. The formula related with the previous chapter. So I'm just recalling it to you. Relation between angular acceleration and tangential acceleration. Now have a look at that. Suppose a body, a particle is moving in a circular path, radius r, of radius r. It is moving in this path with some angular velocity omega. Do you know that it has some tangential acceleration? This one. This tangential acceleration is denoted by A, or someone may represent it as A tangential, T for tangential. So what is the value or what is the relation of this tangential acceleration with the angular acceleration? Angular acceleration is denoted by alpha. After some time, this particle will be here. After some time, this particle will be here. Particle is revolving now. So its position will change. So the tangential acceleration will be like that. Will be like that. So what is the relation of this tangential acceleration? So the relation is tangential acceleration is r times of alpha. This is tangential acceleration. R is the radius. Alpha is what? Alpha is the angular acceleration. I think you know the terms. Alpha is the angular acceleration. Now, moving further. So we will do the concept test later. First of all, we will do some one more concept we are taking here, that is equilibrium of rigid bodies. Mechanical equilibrium of rigid bodies. What is the meaning of equilibrium? What is the meaning of equilibrium? Now, just listen to me. These things are very important actually. When we say equilibrium, for example, for a rigid body, There are two types of motion. One is translational motion and other is rotational motion. So if the body is in both the equilibriums, in translational and in rotational, then it is said to be in mechanical equilibrium of the rigid body. Listen to me again. So for mechanical equilibrium, you can say there are two types of motions. So for the equilibrium, there must be two types of equilibrium. I will tell you one by one. One is translational equilibrium and another is rotational equilibrium. Clear? So what is the meaning of translational equilibrium? That is the very famous term, translational equilibrium. What is the meaning of this translational equilibrium? I will tell you that body should not be moving, should not be having a linear acceleration. Then it is known as translational equilibrium. That means for translational equilibrium, its acceleration should be zero. For rotational equilibrium, the angular acceleration should be zero. I think it is clear. For translational equilibrium, acceleration should be zero. For rotational equilibrium, angular acceleration should be zero. And from Newton's law, you know that acceleration is zero when force is zero. When you can say net force on it is zero. In the same way, the alpha will be zero when net torque on it is zero. So after the discussion, what we can conclude is that for translational equilibrium, net force on a body should be zero. And for rotational equilibrium, net torque on a body should be zero. Or you can say for mechanical equilibrium, both of these things should be zero. For mechanical equilibrium, both of these things should be zero. I think clear. All things are clear and sorted. Moving further. Should I? Now I will take some examples of this mechanical equilibrium of rigid body. Okay, so there is a first question on your screen. Two small kids, pause the video and try to do it with yourself. Just give it a try actually. Because, and one more thing, I don't think that things are live now. So you can pause the video actually, what I can say. Because there is some technical problem. So the video is not live on YouTube, I think. So what you can do, you can pause the video here. Let me check again if it's live or not. No, it's not live. Okay, so no issue. So two small kids weighing 10 kg and 15 kg. These are the two small kids are trying to balance a seesaw. Do you know about seesaw? That every January must have these seesaw things, small seesaws where children go up and down like that. Of length 6 meters. First of all, I am going to draw the seesaw only. So this is the kind of seesaw you can see here. This is the seesaw. And do you know that seesaw is balanced at the midpoint somewhere with the fulcrum at the center? What is the meaning of fulcrum? The axis about which it rotates. So this is the fulcrum. Okay. The total length of the seesaw is what? 6 meters. Now, if 10 kg kid is sitting at one end, so this 10 kg kid is sitting at one end. This is 10 kg. Where should the other sit? Now, can you see that if this person is sitting here, then the fulcrum will what? This setup will rotate like that now. You can see that thing, see those things actually. That this seesaw will bend like that. So what will be the situation for the second person to sit? He must sit somewhere on the right side of the seesaw. So I have placed the second kid, this is of 15 kg, on the right side. Now, let's assume few things. First thing is, let's assume his distance from the center as x. This is the distance of the second kid. Okay. Another thing, can you see that weight or the force that this 10 kg kid is exerting here will be mg. 10 kg and v is what, 10. You can see that 100 Newton force will be acting here and 150 Newton force will be acting here. I think it is clear to you. Now, what I can say, this is the seesaw and they are trying to balance the seesaw. Balance the seesaw means it's not rotating. It's just balanced. Balanced. Balance means it's in equilibrium. That thing you need to know. Now, remember one thing. For equilibrium, what we have studied, that net torque should be zero. Net torque should be zero. So first of all, identify the number of forces. You can say there are two forces actually. One force, there will be another force actually, that will be the reaction force, but we are not going to deal with it right now. One force that you can see is 100 Newton, another force is 150 Newton. So the net torque on the system should be zero. And torque is taken about an axis. So now this is a trick actually. The force that you don't know. I don't know the reaction of the fulcrum. What is the reaction of the fulcrum? This is another thing that sir is discussing, that which we don't know actually. For example, just imagine you are putting this pen on your finger, clear? On your hand or on your two finger, whatever you want to say, and you are just applying forces from the two ends. From the two ends. Can you feel the force on your two fingers? Can you feel this force? If your these two fingers are feeling some force, they will also exert a force on the pen. This force is known as reaction force or the normal force, you can say, but reaction force is a good word, good term to use here. So reaction force. And we don't know the reaction force. We can calculate that. That's quite easy. We can easily calculate that force. But now, right now, we are not interested in that, according to the question. So the force that you don't know, you can choose the axis at that point. For example, the person is a kid is sitting at A, another is sitting at B, and C is the center. So now net torque is what? Suppose torque of this 150 Newton force is tau 1 and torque of this 100 Newton force is tau 2. Two forces are there and we are taking torque about C. So I am writing it, taking torque about C. Okay. Now, if I take the torque about C, can you see that? Just look at that. The 150 Newton force, where will it rotate the seesaw? You can see that if I apply the 150 Newton torque, it will rotate in this direction. In this direction, can you see this is clockwise direction? So this torque is going to be positive torque that we have studied. We have assumed the direction. And this 100 Newton will rotate the seesaw in this direction. This is anti-clockwise direction. So anti-clockwise torque we are going to take as negative. So net torque is what? Tau 1 plus tau 2 is equals to 0. And tau 1 is what? Positive. tau 2 is what? Negative. So can you see that tau 1 is equals to tau 2? Now we can place the value of tau 1 and tau 2. Tau 1 is what? This is the axis. Again, can you see that this is the axis about which the seesaw will rotate? And this axis is in the Z plane. You can see that now in the Z plane. And the force is perpendicular to it, but not intersecting. This is the case number third. Then what we need to do, we need to do the or calculate the torque by force into perpendicular distance, mutual perpendicular distance, and mutual perpendicular distance of the axis is what? 3 meter. So tau 1 is 100 into 3 is equals to tau 2 is what? Force is again 150 into distance is what? So x will be 2 meter. X will be what? X will be 2 meters. I think this is clear to you. Again, moving further. Now, there is another question on your screen. A uniform rod of length L, mass M, is hung from two strings of equal length from a ceiling as shown in the diagram. So, this is the ceiling and two strings. These two strings are used to hang a rod of mass M and length L. Okay. Determine the tensions in the string. This is a very good question actually. Now, imagine. First of all, we will draw the some sort of rough FBD of the things of the forces happening here, of the forces thing on the system. So first of all, you can see that this is a string and there will be a tension. Let's suppose this tension is T1. On the second string, let's suppose the tension is T2. Okay. We need to calculate these tensions. Another thing is there will be a gravitational pull. Na? The rod has a mass M, so its weight will be mg. You know that, and weight mg will act where? At the center. So this is what mg, and you can see that this distance will be L by 2. L by 2. Now this whole setup is hanged by the ceiling, from the ceiling. It will not move actually. You can see that two strings are there, they are inextensible, so it will not move. So it will be in a translational equilibrium as well as in rotational equilibrium. So when it's in equilibrium, then you can say that we can apply two conditions here. One is net force 0, another is net torque 0. Okay. So first of all, for translational equilibrium, are you able to identify whether it is in translational equilibrium or not? Mechanics is what? Is just your imagination power. How quickly you can imagine things. If it is hanged from the ceiling, then it cannot go, it cannot move, it's just hanged. So just cannot move, then it means it has no acceleration. So that's why I'm applying translational equilibrium. For translational equilibrium, what we have learned that F net is equals to 0. How many forces are acting on the rod? One force is T1 that is acting upward, another force is tension 2 which is also acting in the upward direction, and another force is mg which is acting in the downward direction. So what can I write? Taking upward as positive force, I can write T1 plus T2 minus mg is equals to 0. Can you see those things? T1 is upward, T2 is upward, and mg is downward. Another thing, let it be equation number first. Now, or you can say T1 plus T2 is equals to mg, you can place anytime. Now for rotational equilibrium, I can change the pen here. for rotational equilibrium. What should be the term that is going to be zero? You will say that tau net is going to be zero. Another thing that you need to decide about which axis you are going to take the torque, about which axis you are going to take the torque. Then another one pro tip is always try to minimize the number of variables. Always try to minimize the number of variables. For example, what are the variables? That variables are the things that we don't know. So T1 is a variable that we don't know. T2 is a variable that we don't know. So try to minimize these variables. What if I say that I am taking torque about point A? I am taking torque about point A because equilibrium means it is not rotating about any of the axes. So I can choose axis anywhere. So what if I take torque about A? In that situation, the torque of T1 will be zero because T1 is acting on the axis, or you can say T1 is intersecting the axis. That remember those three punchlines that we have discussed at the start of the session. Those three punchlines. T1 is what? Force whose torque is to be calculated. And T1, if you see that this torque is intersecting the axis, in that case, its torque will be zero. I think things are sorted. So I am taking torque about A. So T1 will be eliminated now. Only T2 will remain so that it can be calculated easily. So now, what will you write? There are three forces, 1, 2, and 3. Let's suppose its torque is tau 1, its torque is tau 2, and its torque is tau 3. Now, just decide which torque is positive, which torque is negative. I have told you. If the force tries to rotate the body in clockwise direction, then its torque will be taken as positive. That's our choice. Someone else may decide opposite to that I have decided. So, body is going to rotate about A. Can you see that? This is the rod. And this is end A. This is the midpoint, which is MG wala point. And can you see that we can place another point here as C? We can name it as C. This point is as C. And C is what? C is this point. Now, listen to me. MG is acting here. MG is acting at this point. If this MG is acting here, the rod will definitely rotate in this direction. No? So this MG will rotate the body in the clockwise direction. Can you see that? If you can see that, then it's quite obvious that tau 2 will be positive. Again, if I change the pen or change the color of the pen, then you can again see, have a look at that T2. This T2, have a look at that. This is the rod. I think this is visible. I think this will be quite more visible, na? I hope so. This is the end A that I have holded here. This is end A. And this is point C. And point C is pulling the force. At this point, tension is in the upward direction. So it will rotate in the anti-clockwise direction. In the anti-clockwise direction, it will rotate by the torque 3 in the anti-clockwise direction. So this torque will be negative torque. And tau 1 is what? 0. So net torque we can write. So tau 1 is 0. Tau 2 is what? Minus tau 2 and plus tau 3 is equals to 0. So can you again see that tau 2 is equals to tau 3? Now, what is the value of tau 2? Tau 2 is force into mutual perpendicular distance. That is force of gravitation is mg. Mutual perpendicular distance is what? A to this point, that is L by 2 is equals to tau 3 is what? The force is T2 into the mutual perpendicular distance is, can you see that this is the mutual perpendicular distance, that is 3L by 4. You can see that L will cancel out. So the T2 will be, it will also cancel by 2. That is 2 mg by 3. I hope the calculation part is good. T2 is what? 2 mg by 3. This is what T2 is. Now, can you solve T1 from equation 1? From equation 1, T1 will be what? T1 will be what? Mg minus T2. Mg minus T2. T2 is what? 2 mg by 3. So T1 will be mg by 3. These are again a very good question. You need to understand things. What are the things happening? Now there are a lot of variation of these questions. There are a lot of variations of these questions. You need to practice them. I can't solve more than that. But I have tried a lot to clear the concept actually. So now moving further. Okay. Now take a concept test actually. It's time for the concept test. And these are again very good questions actually. Look at that. There is a question on your screen. Study it. Have a look at that. These all are previous year questions. So make sure, I have not mentioned the date, but it doesn't mean that these are not the PYQs. These are the conceptual questions. The question says a uniform rod of mass m and length L can rotate in vertical plane. Okay. Now in vertical plane. First of all, the vertical plane is what? This is the vertical plane. It can rotate in this plane. For example, again, this is a rod. It can rotate in vertical plane like that. It can rotate in the if it says it can rotate in horizontal plane, that it will rotate like that. These are the things that you need to discuss, that you need to know actually. Clear? This is the vertical plane. Another thing, about a smooth horizontal axis hinged at H. That means at the point H, there is a hinge. This is the hinge. You know the hinge, na? Okay. Find its angular acceleration just after it is released. You need to find, okay. Now listen. I am holding this rod and on a smooth hinge. The hinge is smooth. I am holding it like that. If I release, if I remove this hand, it will go like that. Can you see that? It will go like that. So what are they asking? They are asking that calculate the angular acceleration just after it is released. That means at this point, when I am releasing it, calculate its angular acceleration. Listen to me very carefully. This is again a very good question. Solution. Okay. The body is hinged at point H and its mass is m and the length is L. That's given to us. That's what everything we know. Now, what if I say I need to calculate alpha? I need to calculate alpha. So first of all, bring a relation that is related with alpha, that includes alpha. So I will say that we know that tau is equals to I into alpha. That's the Newton's second law. Nothing else. This is Newton's second law. One more thing. What is torque and what is I? In this situation or in Newton's laws of motions, this is torque and this is I. I is the moment of inertia about the same axis, about the same axis of rotation. And the axis of rotation, can you see that axis of rotation is this? This is the axis of rotation, Z axis. Now, first of all, now what brings this rod in the downward direction? What brings this rod down when I leave it? You can say, sir, gravity is there, na? So gravity is the only one which is trying to, or which is pulling it down, which is moving it down. So first of all, we need to identify the gravity. So gravity is acting somewhere at the midpoint. This is the mg. So only the gravity is the one force which is creating the torque. So now calculate the torque. You will say mg and the mutual perpendicular distance. This distance will be what? L by 2. Clear? So torque is mg L by 2 is equals to. Now what is the moment of inertia of the rod about this axis? This is what? Axis of rotation. In which axis? Z axis. So moment of inertia, you have learned about the center. Center, it's about the center. The moment of inertia of the rod is ml square by 12. And we have also calculated moment of inertia about the end point. And that was ml square by 3. ml square by 3. You need to remember those things. Huh? So I is what? ml square by 3. We have calculated it by using parallel axis theorem into alpha. So can you solve that? I can easily solve that for you. That m is going to be cancelled out. L will cancel the L square. So alpha is what? 3 by 2. 3 by 2. G is still there. L will reach from here. So alpha is what? 3 by 2 G by L. Make G more interesting. 3 by 2 G by L. Is it clear to you? I hope that these things are clear. Second part, B part says tangential acceleration of its free end. The free end is this one. And tangential acceleration, when it revolves, it's just going like that. So tangential acceleration is what? Is this one, tangential acceleration. And we have the relation A tangential is equals to R times alpha. What is R? R is the radius. R is the radius of the circular path. Can you see that? That this circular path has a radius of L. This circular path has a radius L. So I will just place the value A tangential is equals to R is L times alpha. Alpha is what? 3 by 2 G by L. Again, L will cancel out. Tangential acceleration is 3 by 2 G. Is the question clear to you? This is again a very good question. Remember, whenever it is asked to calculate the angular acceleration of a rigid body may be of any shape, It may be of disk, it may be ring, it may be anything. Then you need to apply tau is equals to IL. You need to find the torque and I about the same axis about which the body is rotating. Clear? Moving further. If you have any doubt, you can message me and send anything. Now, the question says, again, this is a good question. It will clear more concepts in your mind. A uniform rod. A uniform rod of mass m and length L can rotate in vertical plane. Again, the vertical plane about a smooth horizontal axis hinged at A. That means axis is again at A. So this is our axis. This is axis of rotation. Or which axis? It is in Z direction. It is in Z direction. Now, find its angular acceleration when it makes an angle theta with the vertical. Now the situation changes. The previous question says find the angular acceleration at the time just it is released. Now it is saying the rod is here. They are saying the rod is here and it is rotating like that, like that, like that. Again, gram. So during this time, you need to calculate the torque. You need to calculate the torque during this time. Okay. So will the rod look like that? The rod will look like that now after the making an angle theta with the vertical. So the angle theta is what? This is angle theta. Clear? Again, one thing, what you need to do, what you need to do, what you need to do. First of all, if I say you will start, I'm not doing anything. Who is putting it down? The gravity is putting it down. So first thing that I will write that tau is equals to I alpha. Torque and I, both of these should be calculated about the end A. Clear? Now, for the calculation of torque, if I say, say, this is the center of the rod, then the mg will be acting here, m and g will be acting here only. I think this is clear to you. Another thing, this is the force. Can you see the axis of rotation is z axis? Again, the same situation. Can you see that force is in the y direction? Y axis. Axis of rotation is z axis. Can you see that both these axes are perpendicular to each other and they are not going to intersect here? They are not going to intersect. These are the skew lines. This is again the third case of torque calculation. Again, the third case, what was that case? The case says calculate the torque by force multiplied by the mutual perpendicular distance. So the mutual perpendicular distance between these two axes is this one. This is the mutual perpendicular distance, which is denoted by R perpendicular. Can anyone solve this? You will say, sir, this angle is theta. I will draw some lines here. This is the vertical line. And this is the rod. I am drawing the center line just to visualize the angles actually. Now, can you see that if this angle is theta, then this angle will also be theta. And this distance is known as R perpendicular. So what is the value of R perpendicular? Can you see a right angle triangle here? Right angle triangle, this is theta. The opposite side will be perpendicular. Then perpendicular will be hypotenuse into sine theta. Hypotenuse is what? This distance is what? Hypotenuse, that is L by 2 hypotenuse into sine theta. Now I am just placing the R perpendicular for the purpose of torque calculation. So torque is what? Force. Force is what? mg into R perpendicular. And R perpendicular is what? I will write as R perpendicular into is equals to I is what? Can you see that moment of inertia of the rod about the end point is m L square by 3 into alpha. mg, can you say m will cancel out? It will be g into R perpendicular is what? L by 2 sine theta is equals to L square by 3 alpha. Again, you can cancel few things here. L will cancel the L square. So the alpha will be, this 3 will go there, 3 by 2 G by L sine theta. I hope the concept is pretty much clear in your mind. So I'm not saying that you need to remember this question. You need to remember the concepts here. So what we have learned in today's session, actually, we have learned how to calculate torque in different scenarios. And you have seen that in most of the situations, the third case is very important. The third case is very important, but you need to remember all those special cases, all those punchlines here. After that, I must say the second part. Okay, there is a second part as well. Okay, it's not a big deal. Second part says tangential acceleration of its free end, tangential acceleration of its free end when it is horizontal. When it is horizontal. So what you need to do? If the rod becomes horizontal, this is the rod. At this time, it is making an angle theta with the vertical. Now, if it becomes horizontal, then the theta will be 90 degree. So, in this situation, can you say that theta will be 90 degree? Theta will be 90 degree. If I place this theta equals to 90 degree in this alpha, so the alpha will become 3 by 2 G by L, and sin 90 is what? 1. From where this 1 came? From the sin 90. Is it clear? Moving further. Moving further. If we know the alpha, then can you know that tangential acceleration is what? R times alpha. R is the length of the rod. Again, I will put the values. So A tangential is L into alpha is what? 3 by 2 G by L. 3 by 2 G by L. L will cancel out. So the acceleration tangential will be 3 by 2 G. So these are the answers of the question. I hope all these things are clear in your mind. Can we take one more question if time allows? Time is itself over. It's over 10 minutes by 10 minutes, actually, I think. So I'm not going to do, I can give it to you as a homework, actually. Again, this is the most important question. These two questions are there, and you can take a screenshot of those questions and try to solve it out. If you are feeling some difficulty in solving those questions, then I will solve it out. One more thing that you need to know, this is a flywheel, and flywheel is nothing but a disc. Flywheel is nothing but a disc. In the next session, for the first few minutes, I will ask you few questions and you need to answer them. That's mandatory so that I can get what I'm teaching is getting up to you. Clear? So right now I am just ending the session. Hope for the best. And I hope you are getting all these things. Let me know. Bye.